Let's have a look at quite a powerful diagnostic tool in determining experimental structure of organic compounds, and this is Proton NMR, nuclear magnetic resonance. Notice that we're going to deal with talking about hydrogen atoms as being protons, as being hydrogen nucleus. For this isotope of hydrogen that we're dealing with a mass number of 1, then obviously all that it's got in it is a proton in terms of its mass. There are no neutrons in there whatsoever. And if we're dealing with the hydrogen nucleus, then of course we're not going to be dealing with any electrons. So describing them as protons is fine in this, and that's why it's called Proton NMR. You can have a wee look at the theory of it at the moment. We're not going to go into this in too much detail. It's far better to just start hitting the ground running and how are we going to use this and look at NMR spectra and decide what's going on in a molecule, or indeed when given a molecule, have a look and think how would I sketch an NMR spectra. And it would be sketching it. It doesn't have to be absolutely accurate. It has to be in the ballpark figure of what we're looking for. So I've posted a wee link to this, so you can go in and have a wee look at it, only up to the low resolution NMR, and just a wee bit about the TMS, the tetramethylsilane, that is used to kind of set the bar at 0, if you like. Very highly shielded hydrogens or protons in here. So we assign that, as you can see in the wee bit up here, we can assign that as a value of being 0. And what we're going to say is that every other really hydrogen environment that we ever find, proton environment that we ever find, is going to be slightly more de-shielded than that. So therefore, we're going to shift up to higher numbers. That's why it's called the chemical shift. And that you don't really need to get into the ins and outs of it. Sometimes people get themselves too caught up and really trying to understand it. That's fine, trying to get your head around it, but what we're interested in is how can we use it. That's the first thing to get on it. So we'll go through a couple of examples in here. So at page 17 in your data book, that's going to be absolutely crucial for this, because that's where all the values are kept. Initially, this can look like a very, very frightening page. There's no doubt about it. But really, you're going to be able to use it fairly well once you get your head around what they're asking you to do in it. Some of these things that are in it we're never really going to see, to be honest. But we'll have a wee look and see what we can do with some getting along. So as we start going through these, and every time that we look at organic molecules now, and remember, even since National 5 and we're through to higher, there are a lot of different types of molecules that we need to know, starting from basic alkanes, working our way through alcohols, carboxylic acids as we head into higher, ketones and alkanals and esters and all sorts of different things in there with functional groups and all the rest of it. So we're really got to familiarise ourselves with all these things. There's no point in Proton NMR. It can get a wee bit lost if you don't have the basic details of what sort of functional groups are going to be found in an alkanol, for example, the OH group, or the carboxyl group in carboxylic acids. Because when you start to go and look at these, and right away you're seeing some functional groups in there. You can see the carbon-to-carbon double bond in here. You can see carbonyl groups up here near the top, etc. You can see OH groups down about here. So obviously there's a lot of information. I'm just doing that. There's the OH groups down about here, etc. So there's a lot of information being given in this, but you really need to know your functional groups. So as we start to work our way through this, every single time really that we start looking at organic compounds, relatively simple organic compounds, then we want to correctly identify the different environments protons find themselves in. Okay. Following on from that, we want to identify the numbers in each environment and why we need to do that. And last but not least is correctly attribute the correct chemical shift to each environment. As we go through these examples that I'm going to do here and leave you a couple to do at the end, that's the order in which I'd like you to do it. Just get the first bit correct. What's the number of different environments here? Hopefully identify the number of number of hydrogens, protons in each environment. And then if we go to page 17 and get a rough idea of what the chemical shift's going to be for each, that would be good. Okay, so we'll start off with methanol. So I've given you the actual answer to this sitting up at the top there. We should be able to see that there are two environments in which hydrogens find themselves. There's these three hydrogens here, which are all in the same environment. They're all attached to the same carbon. And we've got this hydrogen here, which is in a completely different environment because that's chemically bonded to an oxygen. Remember, even from National 5, that we've got a big, and from higher particularly, we've got a big electronegativity difference in here. Oxygen is quite a highly electronegative. So there's going to be quite a bit of de-shielding going on for this hydrogen here. And that's why that sits at a higher value here. The more de-shielding there is, the more we head up here, and the higher the chemical shift goes. So we can see that we should only see two peaks in this, and we do. There's a peak here, and there's a peak here, because there are only two different environments. So when I go back, I should expect to see two peaks in that, because there's only two different environments. Now, what does the numbers tell you in this? Well, we can see that there's three hydrogens here, whereas there's only one here. So when we look at the area under the peaks here, we should see that. Okay, we should see that, being able to, that this peak here, or the area under the peak, it doesn't always mean that it's going to be 3 times as high. You could get that kind of idea going on as well. And the area under the peak here might even be 4 times the area under the peak here. You know, but most times they'll keep it fairly straightforward, or they'll show you some sort of integration in it where they'll do things like this. And you can kind of see that one of the integrations is about 3 times higher than the other integration. Okay, so they'll help you out with those kind of questions with that, if need be. So let's move on now to ethanol. Just get in this, okay. So we should be able to see here that if we're looking for the number of different environments, at this time we're looking at 3. So there's this environment here, there's this environment here, and there's this environment here. Okay, so I should expect to see 3 peaks in this. And furthermore to that, then there's 3 hydrogens in this environment, there's 2 in that environment, and there's 1 in this environment. So the peaks, or the integration in the area under the peaks, should show that. Okay, so here is that's been missed out. This is the tetramethylsilane, which is set to give us a base at 0 with the highly shielded protons that are in that. So if you go to, page 17 of your data booklet, if I skip back just a wee bit, then we can see that these kind of alkane, if you like, type hydrogens, protons, have got quite low. There's not a lot of de-shielding going on in that, because they're not attached to particularly highly electronegative atoms at all. So we're going to have quite a low value in that one, just round about over 1. Now I'm going to draw this, just about here. Let's see, and I'm going to draw it like that. Okay, just as a line at the moment, I can't be bogging into too much in it. But that line's going to represent my 3. That's my 3 hydrogens here. Now, these 2 hydrogens that are on this carbon here are slightly more de-shielded because they're closer to this highly electronegative oxygen in here. So what we're going to find is that value is going to be just a wee bit higher. Okay. Now again, it doesn't really, if you were sketching this, they would be looking for something along this line. So I'm going to say that's my 2 there. So I've definitely got 2 lines in so far to represent the 2 environments that the hydrogens are in, and I'm showing it in terms of the integration as a 3:2 ratio. And then somewhere up about here, we're going to have our single hydrogen from here. Okay, now again, that's a lot more de-shielded. It's going to have a much higher chemical shift because it's attached to the highly electronegative oxygen atom. Okay, now there is the actual kind of shift that you get from that. So you can see they've put that OH just a wee bit higher They've got this one up a wee bit higher than I have, and they've got that one left at the same place as it is. That's okay. You know, if I drew this in an exam, going by the values on page 17, that's absolutely going to get me my mark, okay? Right, let's kick on to where, again, NMR would be really, really useful in terms of this. So we have propanone and propanal. We should remember these things from higher. That we can obtain them with oxidation of, in propanone's case, a secondary alkanol, propanol, and in propanal's case, with a primary alkanol. And we still talk about oxidation, obviously, as one of the chemical reactions. We also talk about reduction much more at advanced higher. So we would oxidise these alkanols with a quite a strong oxidising agent like acidified dichromate or something to get the corresponding carbonyl compounds. These two things are isomers of one another. We could use a chemical test and getting a silver mirror and all those with it's escaped me now even the name of it. I'm going for Phelan's solution there. The silver mirror, oh good grief, anyway it'll come back to me in a wee bit, but that's beside the point at the moment. So how are we going to distinguish between these in terms of the NMR? Well, it's going to be a very, very clear distinction absolutely between these, because if we look over here at propanone, we're going to find hydrogens in this environment, hydrogens in this environment. But when we look at it closely, we'll actually see that all 6 of these hydrogens are in the exact same environment. All 6 of them are on a carbon that's next to a carbonyl group. So that's the key thing that's going to be in this. So all we're going to see in that is one peak. And if we were to duck back to this and start looking here, this is where we're going to start to see these peaks. There's the carbonyl group here, and what we're looking at is a ketone, and you can see it's going to lie somewhere between 2 and 2.7. So again, if I'm sketching this, all that they're going to be looking for in that would be, I would go right somewhere around about here, and I'm going to have a pretty high peak in here, because that's going to represent, I wouldn't need to put that number 6 in incidentally, but that's going to represent quite a high peak in that. So if we jump over here to propanal, which is an isomer of propanone, we're going to see a much different peak in this. So a much different NMR spectra. This time we're going to have 3 different environments for a hydrogen. And not only that, but by the times we do the integration, they're going to have different areas under the peaks. Again, we shouldn't be surprised to see this 3-1 just sitting around about the 1 mark, a wee bit slightly above it. Again, we wouldn't need to put the number in. The 2 mark is going to be slightly more de-shielded, okay, because it's lying much closer over to this oxygen where it is. So again, I'm going to put it around about here. I'm not going to argue too much about that. And I'll put that down as the 2 value. Where we're going to see a big difference in this is in the last hydrogen, because if I go back to page 17, then I'm going to find it a way down. I've lost what, oh, there it is there, okay. So there is the hydrogen that's part of the aldehyde functional group, and you can see that for reasons you don't really need to go into, that that's massively de-shielded, and that's going to lie a way up about 9. So much so that I think in the wee NMR that I've copied to put in here, that I'm not even going to be able to put it in. So I'm going to jump away up here, but this would be sitting as a single peak, a way up high there. Okay, we'll make that as part of that NMR here. So if I was given something that had the formula C3H6O and was asked through an NMR to decide whether that was going to be an aldehyde propanone or propanal, it would be pretty clear for the NMR which would be which. They are vastly different from one another. Okay, so there's a couple there, that I don't couple here that I just want you to have a wee look at for yourself. That we should recognise this as being methyl ethanoate. We did that at higher. So again, go and have a wee look at what's the different environments that they find themselves in, what's the number of hydrogens in each environment, and go and look at page 17 and make a wee stab at where you would put these lines in there. And last but not least, there is a wee family in here. We'll get to naming them later. I'll just tell you that that is an ether with that typical look of the ethers with an oxygen but it's bonded between two carbons. So you can go again and have a wee look at that. But the main thing is we take these things in order. How many lines am I going to see due to the different environments? What integration, what sort of height, what area under the peak am I going to give to each different environment? And last but not least, can I, within a range, in a reasonable, kind of guess, if you like, can I put it at the correct chemical shift? Okay.